Good afternoon, everybody. We are today going to cover lecture number 22 in our series on power devices on silicon and wide bandgap semiconductors. Again, I'm with the Ohio State University, and I have my colleague Dr. Arash Salami here, who has helped me tremendously in developing this course. And this video course has been supported by Office of Naval Research. So, in the last lecture, we talked about the planar DMOSFET, and we took an example of 1700 volt devices, and we calculated the epi layer thickness and doping, and then we optimized by means of simulation the JFET gap, which came out to be about 2 micron for the full cell and 1 micron for the half cell. So, today we will talk about output characteristics and how they relate to the short circuit performance, and how we can optimize the short circuit performance of these MOSFETs. So, to introduce the topic, we have taken our design of half JFET width of 1 micron and channel length of 0.5 micron, and we have simulated our half cell for different gate voltages, and you immediately see that at gate voltage of 20 volt, you can see that the curves bend over here, and then the current keeps increasing as we increase the voltage. So, this part of the curve is called the output conductance, and we do not want this current to be very high at the breakdown voltage of 1700 volt. And the reason is, let us say that we are using this device at around 1000 volts to 1200 volt. Then, if there is a short circuit across this device, that means we have full voltage of 1200 volts is applied, and we have full gate voltage applied, then the current in this device would be very high. So, current here is roughly for 7 times 10 to the minus 5 amps. So, that is 70 microamps. And remember, this is just half of a cell. In reality, this current would be very high because we have thousands of cells in a device. And we know that our operating point is around here, which we will show you later in the on state. So, the current could be 10 times higher if the device happens to get short circuited and the full voltage on the drain source gets applied to it while the device is on. We can have a lot of current flowing. This kind of current density can create a lot of heat in the device, and that heat dissipation will raise the temperature of the device, and when the temperature rises about 1000 to 1200 degrees C, you will see that the aluminum starts melting at around 600 and 60 degrees C, and then there is lot of other thermal stresses, and you will see that most of the device will be destroyed thermally, and this is called the short circuit withstand time. So, let us say the device gets destroyed in few microseconds, then that is the time we have for us to detect a short circuit and turn off the device by applying the 0 gate voltage, so that we can save the device in a circuit. So, the standard is 10 microsecond. We have to be able to withstand for 10 microsecond in most silicon power electronic circuits. And the key of that is to reduce this current by essentially device engineering. So, in this case, our selected design with half micron channel length and half JFET width of 1 micron has a current flowing at 1200 volts, which is of the order of 10 times the operating current at low drain voltages. And ideally, we would like to reduce this current and make this curve flat, like shown in with the green line there. And the reason this IV curve has an output conductance like this is because of the short channel effect. The channel is only half micron, and if we apply a very high drain voltage, that comes up to the JFET region and starts affecting the channel length, because that high field at the edge of the channel length will have an effect of reducing the effective channel length, and that is why this current keeps on increasing at high drain voltages. So, here what we have shown you in this simulation is that we have kept everything constant, except we have changed the channel length to from 0.5 micron, which was our standard design, to 0.75 micron, 1 micron and 1.5 micron. And you can see by increasing the channel length, we reduce the effect of drain voltage on the channel length reduction due to the drain induced barrier lowering, and the curves come down and become flatter. So, we can reduce this current quite a bit and thus increase our short circuit time to 10 microsecond or beyond by doing this, by increasing the channel length. Now, the problem with increasing the channel length is that if we look at the on-gate output characteristics versus channel length at a full applied voltage of 20 volts at low drain voltages, you can see that the current at the operating point, which I should say is about 1.5 volts right here, decreases by about 50% by increasing the channel length from 0.5 micron to 1.5 micron. This means our on resistance goes up and the device size becomes bigger, and the cost goes up because of that. So, this is not a preferred solution, because the device cost will go up and the device size will become bigger if we increase the channel length. So, another method has been suggested in the literature, and that is called the shielded DMOSFET. And in shielded DMOSFET, at the bottom of P well, we increase the doping to 1E19 per centimeter cube, as shown by this red region. And let us say this red region is about 0.2 to 0.5 micron thick. So, remember, PE well is made by ion implantation of the p-type impurities, and you will see that in the next lecture how we actually make this device. But it is good to remember that at most we can make the depth of p well to about 0.7 to 0.8 micron using standard ion implantation energies of 360 keV. So, while we keep this depth of 0.7 to 0.8 micron, we can dope the bottom of the p well of about 0.2 to 0.5 micron, very high doping, say 1E19 as shown by the red region. And we keep everything else constant, channel length of half micron, JFET width of 2 micron. Then if we simulate the output characteristics again, the black curve is the standard curve without the shielded structure, that is the conventional structure. The red line is the shielded structure where the thickness of the high P plus doping is only 0.2 micron, and the blue represents the shielded DMOSFET where the high doping is over 0.5 micron in the shielded region. And you can see that we can approach the ideal curve with high doping in the shielded MOSFET structure. However, we should realize that this structure also has drawbacks in the sense that it increases the cost, because implanting such a high dose of aluminum at the bottom of the P plus takes longer time, and since these implants are done at high temperature, there is a lot of cost associated with this red area I have shown you. But nevertheless, the advantages are clear that output conductance is reduced to almost 0, or the curves become flat if we are able to put this high doping in the P well. And this then will lead to longer short circuit times. And if you see the on state characteristics at low voltage for those two cases, you can see that the forward voltage drop at the operating point in the on state, say at 1.5 volt, doesn't really change. You get the same on state current at the same forward drop. So, there is no negative impact on the on resistance of this device. So, this is an easy fix for this problem, that you can get high short circuit time without sacrificing the on resistance. The drawback is the cost of ion implantation is high. But this is something we should do, because there are other advantages of putting this high doping that we will discuss later, such as with the ruggedness of these MOSFETs. All right. So, at this point, then this is our structure that we would like to simulate for edge termination. And as we had discussed in the edge termination lecture a long time ago, that one of the popular edge termination structure is guard rings. So, what we have done is simulated a structure with 46 guard rings. The spacing between the guard rings is 0.8 micron, and the width of the guard ring is 2 micron. And this is the last cell of the device. So, basically there are number of cells to the left of this figure, but this represents the last cell of the device, and then we put guard rings, 46 of them. And the idea is, if you remember, that we want to reduce the electric field at the edge of the device so that we can get ideal parallel plane breakdown voltage. So, the idea is to reduce the electric field in this region as opposed to the electric field in the active region. So, this is the active region and this is the guard ring region or the termination region. We want to reduce the electric field in this region below the electric field in the active region, so that when the device avalanches, it avalanches over the active region and not the edge termination, which is important because the active area is large and we will get lot more avalanche energy from this structure. All right. So, if you remember, the principle of guard rings is, as we apply higher and higher voltage, this first guard ring spacing essentially is fully depleted at some voltage, and then this floating guard ring, the first floating guard ring, acquires that potential at which this region is fully depleted. And then as we increase the voltage on the main junction, this guard ring floats up with that main junction by keeping a certain voltage difference, and then the second spacing is fully depleted, and the second guard ring acquires a potential with respect to the main junction and the first guard ring, and then they all go up in voltage as we increase the voltage, and so on to the last guard ring. So, here is the device simulation using the 2D device simulator called Silvaco, and you can see we are plotting the drain current versus drain voltage at gate voltage of 0. So, the device is essentially off, and you can see that at around 1860 volt the device begins to avalanche and the current increases very rapidly for further increase in the drain voltage. So, this area is called the avalanche voltage and avalanche region, and if you recall that in the avalanche region the electrons and holes are accelerating in opposite directions under the applied electric field in the drift layer, and when they acquire enough energy they knock off an electron from the outermost orbit and create another electron hole pair which accelerate again and create more electron hole pairs under this high field, and therefore this is a positive feedback process, just pretty much like the nuclear fission reactor, and the current increases rapidly. All right. So, if we take 850 volts, which is slightly below the avalanche voltage, and but the device is still avalanching, we can look at, so device is at the onset of avalanche at 1850 volt. As you can see, this blue line is 1860, 1850 would be slightly below that. So, we will be biased here somewhere at the onset of avalanche, but we can see how the guard rings are behaving. So, you can see what we have shown you in this simulation is the active area. Here are the 46 guard rings, and here to the left of the green line is the active area. So, here is my last cell and then the guard rings start. And you can see that avalanche is happening in the active area. You can see that current is flowing in the active area mostly, and very little current is flowing in the guard rings. So, if we plot the electric field contours at 1850 volts, you can see the electric field is high in the active region left to the green dotted line, and then the electric field is reduced to the right. Now, if we draw a line below the guard rings like a cut line and look at electric field along this line just below the guard ring, horizontal line, then if we look at the electric field, that looks like this. So, you can see that the electric field is high in the active region, and then it reduces quite a bit in the first guard ring and keeps on reducing as we go further to the second, third, fourth, fifth to the guard ring number 46. And so, this is good. I think this is a good design. So, we can achieve this mostly because we have kept the guard ring spacing of 0.8 micron. If we increase this guard ring spacing, you can see that the electric field in the first guard ring will rise, and if we make it say 2 micron, then this guard ring will not work. So, you want to keep this spacing as small as you can for these guard rings to be very effective. So, here are the constant potential contours at 1850 volts, and you can see these are 100 volt steps, and you can see that these guard rings acquire potential as we move from left to right, and you can see that the third guard ring maybe is at 100 volts, and then maybe sixth guard ring is at 200 volts, and so on. So, again, if we draw the horizontal cut line at the bottom of the guard rings and look at the potential contour at 1850 volt, we have drawn this red line as a cut line, and we are looking at the potential at the guard rings along this cut line. You can see that we start at roughly 0, and as we go up to the 46 guard rings, we haven't plotted all the guard rings here, but you can see as we move from left to right, there is a constant potential drop between guard rings. So, the first guard ring is perhaps taking on 50 volt, the second guard ring is perhaps taking 75 volts, the third guard ring is perhaps 100 volt, but these are the voltages at different guard rings as we move from left to right. So, we know that this is working, and we will probably now build this structure and show you how the device is made, both in process wise, and also we will do a sample layout for you to show you how these different layers relate to each other. And we'll do the shielded MOSFET. So we'll have this red region here for the shielded part, as we had shown high p-type doping at the bottom of the p-well, and we will form all these cells to the left of this last cell, and we'll show you guard rings on the right hand side and the left hand side and the top and bottom. So we'll show you the layout and the process sequence in the next structure, and this would be a good time to stop today. And next time my colleague Dr. Arash Salami will walk you through the processing and layout of this 1700 volt we have designed. Thank you very much.